Hello, my name is Hebin Kim, and today I will present 3D Gaussian splatting for real-time radiance-field rendering. This paper proposes the use of 3D Gaussians as scene primitives along with a tile-based rasterizer, enabling high-quality real-time rendering. Novel view synthesis is an important research field in computer vision that focuses on generating images from specific viewpoints. NVS utilizes 2D images captured from different viewpoints and aim to accurately represent how an object or scene would appear, even in regions not directly observed in the input images. Previously widely used methods for 3D scene representation included meshes and points, as well as neural radiance fields. Meshes and points represent a scene by assigning attributes to coordinates in 3D space. These points can also be connected along the surfaces of objects to construct mesh representations. One major advantage of this approach is that it is well suited for GPU and CUDA-based acceleration. However, because the method requires densely populating the 3D space with points where objects exist, it suffers from large storage requirements. Another representative method is neural radiance fields, or NeRF. NeRF is a learning-based continuous function that takes a 3D coordinate and camera ray direction as input and outputs the radiance and density at the location. This approach can generate highly faithful rendering results and requires only 2D images and calibrated cameras during training. However, the process of sampling points along camera rays and accumulating their colors and opacities introduces significant computational overhead, resulting in long training and rendering times. Therefore, the authors propose the need for an efficient primitive capable of representing 3D scenes. They argued that an ideal representation should not only produce high-fidelity rendered images, but also enable short training times and real-time rendering performance. The authors explain that using 3D Gaussian splats as scene primitives provides several useful properties. First, the representation is differentiable. The properties of 3D Gaussians can be updated in a fully differentiable manner during optimization. Second, the representation is unstructured. 3D Gaussians can exist anywhere in 3D space and are not constrained by grid-based structures. Third, the representation is explicit. Each 3D Gaussian directly serves as a scene primitive, allowing the scene structure to be represented explicitly. Finally, the method enables very fast rendering. 3D Gaussians can be easily projected into 2D splats, and efficient rendering is achieved using the proposed tile-based rasterizer. The proposed method begins by calibrating cameras and obtaining sparse points from 2D images through a structure from motion, or SFM. These sparse points, referred as SFM points, are then used to initialize 3D Gaussians. These Gaussians are iteratively optimized to accurately represent the 3D scene. In this slide, the properties and formulation of 3D Gaussians are introduced. Each 3D Gaussian is represented using four main properties. First, the mean represents the center position of the Gaussian in 3D space. Second, the covariance matrix defines the anisotropic shape and orientation of the Gaussian. As shown in the figure on the right, the Gaussian can be stretched and rotated differently along each axis. Third, the opacity controls the transparency of the Gaussian during rendering. Finally, the color is represented using spherical harmonics, or SH, which enables modeling of view-dependent appearances. Using these properties, each Gaussian is formulated as a 3D Gaussian distribution centered at point mu with covariance matrix sigma, as shown in the equation below. In this slide, the authors explain how anisotropic covariance is represented in 3D Gaussian splatting. The covariance matrix sigma has physical meaning only when it is positive semi-definite. However, during optimization with gradient descent algorithm, this property may not always be preserved. To address this issue, the covariance matrix is parameterized using a scale matrix S and a rotation matrix R. As shown in the equation, sigma is expressed as R as S transpose R transpose, which guarantees a valid covariance representation during optimization. The figure below illustrates the importance of anisotropic Gaussians. The anisotropic Gaussians can better preserve elongated structures and fine geometric details in the scene. In this slide, the initialization and optimization process of 3D Gaussians is explained. First, a 3D Gaussian is initialized for each SFM points. The covariance matrix is initialized as d²i, where d represents the average distance from a point to its three nearest neighboring points. After initialization, the arrangement of 3D Gaussians and their properties are iteratively optimized to minimize the error between the rendered images and the GT images from the training views. The loss function shown below combines an L1 loss and the SSIM loss to improve both pixel level accuracy and perceptual image quality. The authors introduced the adaptive density control strategy for 3D Gaussians. Since the initial distribution of Gaussian obtained from SFM points may not be optimal, the density of Gaussians is dynamically adjusted during optimization to better represent the 3D scene. This process includes three operations: removing improperly placed geometry, generating new geometry, and relocating improperly placed geometry. First, the process of removing Gaussians that do not contribute to representing the scene is performed as follows. Every 30,000 iterations, the opacity values of the Gaussians are reset to 0. Then, after the optimization warm-up phase, Gaussians with opacity values smaller than a predefined threshold are removed every 100 iterations. This helps eliminate unnecessary Gaussians and improves the overall scene representation efficiently. The authors present two representative cases of improperly placed Gaussians. The first is under reconstruction, where important geometric features are missing because Gaussians are absent from locations where geometry should exist. The second is over reconstruction, where Gaussians occupy excessively large regions and appear in locations where geometry should not exist. The authors observed that both cases tend to exhibit large view space positional gradients. This suggests that the Gaussians must move a relatively large distance from their current positions in order to reach more appropriate locations. As a result, the authors propose a density control strategy based on cloning or splitting across to the gradient magnitude. For Gaussians whose gradient magnitude exceeds the threshold, the method applies either cloning or splitting operations. The cloning operation duplicates a Gaussian with the same size as the original Gaussian. The cloned Gaussian is then placed at a position shift according to the positional gradient. In contrast, the split operation divides a large Gaussian into two smaller Gaussians. Each new Gaussian has its scale reduced by a factor of 1.6. Their positions are determined by sampling two center positions from a probability distribution defined by the original Gaussian PDF. The authors also introduced the tile-based rasterizer. The key idea is to pre-sort the Gaussians in advance. By doing so, the method alleviates the expense per pixel sorting bottleneck that commonly appears in conventional alpha blending-based rendering approaches. Another important advantage is that there is no limit on the number of Gaussians that can receive gradients during optimization. This allows stable optimization even in high complex scenes containing a large number of Gaussians. The proposed rasterizer operates through the following process. First, the screen is divided into 16 × 16 tiles. Next, only the Gaussians that affect the view frustum are selected. More specifically, only Gaussians whose 99% confidence intervals intersect with the view frustum are considered. For each tile, the corresponding influencing Gaussians are collected for rendering. Each Gaussian is instantiated according to the number of overlapping tiles, and each instance is assigned a key consisting of the tile ID and view space depth. The Gaussians are then sorted based on these keys. Finally, for each tile, a tile-specific list is constructed by identifying the first and last Gaussian in depth order among the Gaussians splatted onto the tile. For each pixel, the color value is computed using the color and opacity of the Gaussians, and the process terminates once the accumulated alpha value reaches the target saturation level. During the backward pass, the Gaussians that actually contributed to each pixel color in the forward pass are revisited and identified. To achieve this, the sorted Gaussian array and tile ranges used in the fourth pass are reused, and the Gaussians are traversed in back-to-front order to facilitate gradient computation. The final accumulated opacity obtained at the end of the fourth pass is stored, and the opacity of previous stage is recursively reconstructed using the alpha values of Gaussians in reverse order, enabling the computation of gradient coefficients. To ensure stable optimization, Gaussian training begins with low-resolution images. From 0 to 250 iterations, training is performed using images at 1/4 resolution. From 200 to 500 iterations, half-resolution images are used. Finally, training proceeds with full-resolution images for fine-grained scene representation. Using all SH coefficients from the beginning may lead to unstable or inaccurate convergence. In particular, when some viewing directions are missing in the captured images, the optimization may produce incorrect values even for the zero-order SH component. Therefore, the training initially starts with only the zero-order band, which does not model view-dependent color variants. Then, every 1000 iterations, an additional SH band is progressively introduced during training. To evaluate the performance of the proposed method on real-world scenes, the author conducted experiments on 9 scenes from NeRF, 2 scenes from tanks and temples, and 2 scenes from deep blending. The results show high SSIM and PSNR values, along with low LPIPS values in most cases. These results indicate that the proposed method generates images with superior visual quality. The authors also analyzed the image quality produced at different stages of training by varying the number of optimization iterations. Even at only 7,000 iterations, the proposed method achieved competitive rendering quality. With 30,000 iterations, the generated images were able to preserve fine scene details more accurately. The training speed is particularly impressive when compared to previous methods. Training for 7,000 iterations required only about 5 minutes, while 30,000 iterations took around 35 minutes. In contrast, the neural radiance-field based method, NeRF, required nearly 48 hours of training. These results demonstrate that the proposed method achieves remarkable fast training while maintaining high visual quality. The authors also conducted experiments on the synthetic Blender dataset. This dataset consists of objects defined within bounded scenes and provides accurate camera parameters, making it well suited for evaluating rendering quality and geometric reconstruction performance. On this dataset, the proposed method achieved state-of-the-art performance in terms of the average PSNR value. Finally, the authors conducted an ablation study to verify the effectiveness of each component in the proposed method. First, they compared Gaussian initialization using random points with initialization based on SFM points. Although the random point initialization was able to generate somewhat plausible images, noticeable artifacts remained, especially around detailed geometric structures, even after repeated optimization. Next, the authors analyzed the effect of the density control strategy by presenting results without the split operation and without the clone operation. The split operation was designed to handle cases where excessively large Gaussians occupy broad regions. In the ablation result, the no-split case shows the detailed structures, such as the leaf in the background, are not properly reconstructed. Large Gaussians remain in the scene, resulting in noticeable degradation of the image quality. In contrast, the clone operation was introduced to improve representation capability by adding Gaussians to regions lacking sufficient geometry. In the no-clone example, the absence of this fine-grained supplementation causes detailed structures, such as the bicycle wheels, to be poorly reconstructed. Next, the authors present an ablation study related to the proposed rasterization method. In this experiment, the number of Gaussians updated through gradient during the backward pass was limited to only 10, and the results are shown in the limited BW row. The purpose of the experiment was to determine whether it is possible to reduce the computational cost of gradient propagation while still maintaining image quality. However, as shown in the results, limiting the number of Gaussians receiving gradients caused Next, the authors present an ablation study related to the proposed rasterization method. In this experiment, the number of Gaussians updated through gradient during the backward pass was limited to only 10, and the results are shown in the limited BW row. The purpose of this experiment was to determine whether it is possible to reduce the computational cost of gradient propagation while still maintaining image quality. However, as shown in the results, limiting the number of Gaussians receiving gradients caused significant quality degradation. This suggests that one of the key characteristics of the proposed rasterizer, having no restriction on the number of Gaussians that can receive gradients, plays an important role in the optimization of 3D Gaussians. The final ablation study focuses on the anisotropic covariance of Gaussians. The authors performed the optimization process using Gaussians with isotropic covariance instead. As shown in the example image, this setting imposes significant limitation on representing 3D geometry. Detailed structures such as leaves and branches are not properly reconstructed and instead appear overly discretized. Finally, I'll conclude the presentation by summarizing the key contributions, limitations, and future direction of 3D Gaussian splatting. The authors presented the first approach capable of real-time, high-quality radiance field rendering across diverse scenes and capture environments. At the same time, the method achieves training times competitive with the fastest existing approaches. The key idea is the use of 3D Gaussian primitives. These primitives preserve the characteristic of volumetric rendering for optimization while directly enabling fast splat-based rasterization. Through this design, the authors demonstrated that continuous scene representations are not strictly required for fast and high-quality radiance field learning, which contrasts with the commonly accepted view in previous work. The authors also noted that at present, only the rasterization stage is implemented using optimized CUDA kernels, and the most of the training time is consumed by Python code. They accept that fully porting the optimization pipeline to CUDA could provide significantly greater acceleration for performance-critical applications. Finally, the authors suggested exploring the generation of Gaussians from mesh reconstructions as an interesting future research direction. Since meshes are one of the most widely used scene representations, this approach could provide both practical benefits and deeper insight into the relationship between volumetric and surface-based representations. Thank you for watching.